One of the purposes of this lecture didn't even make it into the title, but I want to go back and review some really key concepts that we'll need for modeling or for building a two-dimensional finite difference time domain code. After that review, nothing new will happen there. After that, I want to talk about how we incorporate metals and some alternative grid schemes. Some of these aren't exactly obvious. We won't be doing a whole lot with the alternative grid schemes in this course, but I definitely want you aware of it and the reasons for going to an alternative grid in FDTD. The key things I want to review for a two-dimensional finite difference time domain code is the PML and its placement, why we need spacer between our device and the PML. I want to review again the two-dimensional total field scatter field formulation, and I want to step you through the computing reflectance and transmittance. So nothing new happens there. I just want you to see that again. Then we'll talk about how to incorporate metals into finite difference time domain, because there's several different techniques. And there's actually a whole lot in their literature on doing that. And I'm only going to touch on the high-level points and the simplest techniques for doing that. But suffice to say, if you want a more sophisticated code, go off to the literature and read what other folks are doing. And then finally, some alternative grid schemes and why we would even be interested in developing a code with a different grid scheme altogether. So we need about a wavelength of space between our device and the PML. We saw that in certain circumstances, devices can have very large evanescent fields. This happens particularly near a cutoff. If we have an evanescent field like we're showing at the lower left here, that evanescent field can pass through where we're recording, in this case, the transmitted fields. So in our diffraction efficiency calculations, we ignore the evanescent fields because we assume they are not transporting power. However, if those evanescent fields touch our PML region where the refractive index suddenly becomes very high, and these evanescent fields can now couple into propagating waves, we can have power essentially tunnel past our record plane here, and we won't record it as transmitted or reflected energy. That's bad. So we need to place the PML away from these evanescent fields so they don't touch. The rule of thumb is to make it about a wavelength for devices that are resonant, a quarter wavelength for devices that are not. However, we really need to watch the simulation, visualize the fields, and see if there is an evanescent field extending into our PMLs, because if there is, we need to fix that. On to the total field scatter field. This is a way of essentially injecting a one-way source. And for me, it's a bit complicated to think how to modify equations to inject a one-way source. So I approach this a different way. And I put it in the framework of total field scatter field. We just define one region to contain the source and the scattered fields. This would be physical reality. And then a scattered field region where we only see the field scattered from the device. We do not see the source. We simply just declare that to be, write our finite difference equations consistent with that, and suddenly we have our one-way source. But I think it makes a bit more sense to kind of come in from behind like that. So if we define these two regions, we know in the scattered field region we should not see any source. However, in the total field region, we see our scatter fields plus the source. So when we're writing finite difference equations in the scattered field, they contain terms from the total field side, which are not compatible with scattered field quantities. And so what we'll do is we'll subtract the source from it to make them compatible. Likewise, we have finite difference equations on the total field side that reach to the other side and contain suddenly scattered field terms. And we have to add the source to those to make them compatible with total field quantities. It's when we incorporate those corrections that we actually implement our one-way source. We isolated our curl calculations, pulled them essentially out of the update equation, so we calculate our curl computations separately. And it's inside the curl computations where we have these spatial derivatives that reach out to to adjacent cells in the grid. So it makes sense. This is where our problems would occur. This is where the corrections have to happen. So let's say we are on the scattered field side and we are calculating the x component of the curl of E. We see we have a finite difference equation that reaches to the total field side. So we have a total field term really sitting in a scattered field equation. This is not compatible and we have to fix that. How do we fix that? How do we get a total field term to look like a scattered field term? We subtract the source from it. So now what's in parentheses looks like a scattered field term. Well, we can factor this correction term out to the outside, and what we're left with is the original curl equation minus a correction term that only has to happen at this one plane. The rest of the curl term we calculate everywhere on the grid. So what kind of cool happens is this tells us we can calculate the curl across the entire grid just like we've been doing, without knowing or considering anything about this total field scatter field source. When we're done that, when we're done the loop calculating the curl, we can set up a loop to just go horizontally across the grid, just across this one row, and subtract these correction terms all the way across the grid after we calculate curl. We have another curl calculation that happens on the total field side. This is the z component of the curl of H. And we see we have one H field term that has to come from the scattered field side. But this scattered field quantity is sitting amongst a bunch of total field quantities. We have to add the source to it. So what is inside the parentheses now looks like a total field term. Similar to before, we take this little correction term, we bring it to the outside, and what we're left with is the original curl calculation. So we can calculate the curl everywhere on the grid without having to consider anything total field scatter field. And then after that, we have another loop that steps horizontally through the grid and subtracts this correction term to that curl quantity. Having done that, we've injected our one-way source. So now we need to calculate the source terms, the correction terms that we have to incorporate into our curl calculations. We need the electric field from the total field side and the magnetic field component of the source from the scattered field side. We know we want a Gaussian source, so for simplicity we'll just set the electric field equal to our Gaussian source. But we need to know what the magnetic field looks like for that same source. Well, we know that the amplitude is different because of the impedance of the material. Otherwise, it's the Gaussian source with a delay, and there's two components to the delay. These two field components are a half grid cell apart, so we need the time delay due to that. They also exist at different times. They're a half time step apart, so we need to include that in here. But otherwise, here's our two equations for calculating the electric and magnetic field components of our source. And we can do this ahead of time before the main FDTD loop. So here's a block diagram of how we would modify the main loop for including this source. The first thing we'll do is calculate the curl of the electric field. So we loop across the entire grid, and when we're done this, and that loop is completely done, we're ready for the next step, then we put a loop that steps horizontally through the grid and incorporates that correction term. Then we know we have a PML, so we have some H field integrations to do, and we end up updating the H field. Then we calculate the curl of the H field. So this loops over the entire grid. When this is done, not inside this loop, when this is done, we then have another loop which steps horizontally through the grid that incorporates these correction terms to the H field curl. Once we have that, we can update our D field integrations. We can update DZ, update the EZ. Maybe we visualize our fields. Maybe there's even Fourier transforms happening. But here's our main loop from the perspective of our total field scatter field source. And the last review topic, calculating reflectance and transmittance. So we have a field going through a periodic structure. That periodic structure chops up the field in all these different discrete modes. We know some of those will be waves, some will be evanescent fields. Each one has its own wave vector, and it turns out these wave vectors can be complex. They can have real and imaginary components. So what did that mean? Well, when we had a purely real wave vector, that meant just pure oscillation and no decay, just a pure sine wave in the direction the wave is traveling. If that wave vector was purely imaginary, it was pure decay in the direction of the wave vector. If it was complex, we saw that we had both. We see we have oscillation, but it decays with distance. So those are the only three things that can happen. And in fact, in electromagnetics, those are the only three things that electromagnetic fields can do. They can oscillate, they can decay, or do both. We talked a bit about evanescent fields, and from this perspective of total internal reflection, here's one way that we can cause an evanescent field. If we have a waveguide, the field outside the guide will be evanescent. So it's a field that's not going anywhere. This evanescent field is not pushing power in the vertical direction towards our boundaries. It is pushing power, in this case left and right, but it's not pushing power away. But we definitely have these evanescent fields. And so resonant devices can produce evanescent fields, waveguides can produce evanescent fields, cutoff at an interface can produce evanescent fields. There's lots of mechanisms that can produce these evanescent fields. And we already know we don't want the evanescent fields to touch our PMLs. So a wave traveling through something periodic, the field amplitude takes on the same periodicity as the structure that it is in. If the field becomes periodic, we can expand it into a Fourier series. Well, a Fourier series is a sum of discrete things. Those discrete things have the same mathematical form as plane waves. So, it turns out, if we have a periodic electric field, we can also think of this as a sum of plane waves all at different angles. And so we call this the plane wave spectrum. And so really, when a electromagnetic wave travels through something that's periodic, that periodic structure chops up the wavefront, and suddenly we get diffraction into these discrete directions. So if we have an applied wave, so k ints, coming into a grating, that grating gives us an infinite expansion of the transverse wave vector component. So in this case, it's the x direction. Each one of these has to be phase matched into our grating. Well, as this transverse wave vector becomes larger and larger and larger, at some point it's too large. It's describing a variation that is too abrupt to match to any kind of propagating plane wave within this region. So it's really only the lower order few diffraction orders that actually put any energy into propagating waves. The rest are cut off, they're evanescent. We can see that there's a field, we can see it penetrates, but it's confined to the surface because it decays away from the surface, and it's varying very fast. And in fact, the higher order we go, the more abruptly that is changing, the less it penetrates into that material. So when we phase match these transverse wave vectors, we then inside this, we calculate the longitudinal component from the dispersion relation. And here we have the square root of a difference of two numbers, so we can have a real or an imaginary answer here. When the longitudinal component is real, we're talking about these plane waves. Those are the only ones we care about when we're thinking about power being transported to or from a device. When this is imaginary, it's cut off. These don't contribute to power being transported away from the device, except for that one exception of electromagnetic tunneling that we're avoiding by placing our PMLs far enough away that they're not touching those evanescent fields. So here was our procedure that we did, recognizing all this. We start with the pointing vector, E cross H. We looked at the impedance of the material to eliminate the magnetic field. We then said it's really only the Z component that contributes to power flow in or out of the device. So we're only looking at the Z component, or the vertical component, of the pointing vector. We then defined diffraction efficiency as the power in the diffracted mode relative to the power in the applied wave. So we're asking ourselves what fraction of power of that applied wave is going into our particular diffraction order, and that is the diffraction efficiency of that order. So, given all this, we lump this together and we can calculate the diffraction efficiencies of all our reflected diffraction orders, and we can calculate the diffraction efficiencies of all of our transmitted diffraction orders. And notice there's this real operation which started up here, but what this is telling us down here is that we are ignoring those evanescent fields. We're only really listening to the power in the propagating waves. Well, once we have all of these diffraction efficiencies, we can add all of the reflected diffraction efficiencies together and get overall reflectance. We can also add all of the transmitted diffraction efficiencies together to get overall transmittance. And then if we add those two together, and if we have no loss or gain, we should equal 1 or very close to 100%. Of course, if there's loss, that conservation will be less than 1. If there's gain, it'll be greater than 1. If there's both, who knows what it'll do. So here's how I visualize the arrays and how we're storing things in memory. So on the left is our finite difference time domain grid. We have our device. We have a spacer region between it and the PML. We have a region where we're injecting our one-way source, so our source just travels downward. Above that one-way source, but before the PML, this is where we'll be recording our reflected fields. And all the way down the bottom is where we're recording our transmitted fields. We call this the transmission record plane and the reflection record plane. Now, for every frequency that we're interested in, and very often we're plotting transmission and reflection versus frequency, and there's hundreds of frequencies. So for every frequency, we store the horizontal width of the grid. If we're interested in 100 frequencies, we'll do that 100 times. And what we'll do during the simulation, we'll be calculating the steady state field in the cross-section of the grid at frequency 1, at frequency 2, at frequency 3, at frequency 4, and so on, up to potentially hundreds of frequencies. And we do the exact same thing on the transmitted side. So these arrays, this one right here, called steady state fields, these are calculated during the simulation. At this point, the simulation is finished, and we're post-processing from this point to the right. We will do an FFT, so we'll take this row, the steady state field, and FFT it. And what we end up getting are the amplitudes of the spatial harmonics of our diffraction orders. And we have the amplitudes for frequency 1, amplitudes for frequency 2, amplitudes for frequency 3, and so on. And we also have amplitudes for our transmitted diffraction orders at each frequency that we're interested in. Now we have all the information to calculate our diffraction efficiencies, but we know it's only the lowest order few that really contribute to power flow. So we only have really numbers here in the middle that correspond to those propagating waves. The rest are evanescent, and we're not listening to those. So now we have our diffraction efficiencies for all the reflected modes at each frequency of interest. We have all of the diffraction efficiency of the transmitted modes at each frequency of interest. Then what we'll do is we'll take this first row and add it all up, and we have the overall reflectance at frequency 1. We'll go to the second row, we'll add all these up, and we have the overall reflectance at frequency 2. And we do that for all frequencies, for the reflected and the transmitted modes. And so what we come away with now are two one-dimensional arrays, which are the transmittance and reflectance as a function of frequency. And we can plot those and visualize those. So here's the overall procedure written out. Step 1, we do our simulation. And we calculate all the steady state fields on the reflected side and the transmitted side, and also the source at every frequency that we're interested in. Once that simulation is done, now we set up a big loop that loops over frequency. So for each frequency of interest, we will perform what is highlighted in yellow here. So we'll calculate the incident wave vector, the vertical component of it. Then we calculate this infinite expansion of the transverse wave vector components. That's the same everywhere. And if we have 21 points across our grid, we'll have this array M that will go from -10 all the way up to +10. It passes through 0, so we'll have 21 points. Given that array M, we'll have an array KX, which is our transverse wave vector components. And these will all be real. Given that, we can use the dispersion relation and calculate that vertical component of the wave vector for each spatial harmonic. But the reflection and transmission regions can be in different materials, so we need to do this twice. So now we have new arrays for the longitudinal components of the wave vectors, and these could be real or imaginary. Then we will take our steady state fields at each frequency and divide by the source at that frequency. We know that the power in the source dips off as frequency increases, and we don't want that artifact to be in our steady state field, so we divide to sort of normalize that. At this point, it looks like we've had a unit amplitude source at each frequency. We then take those steady state fields and we FFT them to calculate the amplitudes of our spatial harmonics. Once we have the amplitudes of the spatial harmonics, we have all the information we need now to do our diffraction efficiency calculations. At this point, we'll know the diffraction efficiencies of each spatial harmonic at each frequency. We add up all of the reflected diffraction efficiencies, and we get overall reflectance. We add up the diffraction efficiencies of all our transmitted modes to get overall transmittance. And then we add those two together to get our conservation. And this should equal 1 if we don't have loss or gain in our model. If it's not, that's a sign that something is wrong. Okay. So that's our review of what I think are some of the key points so far in our FDTD. So now on to some new material. And we want to talk about how to incorporate metals into FDTD. So, well, first of all, what are metals? They are things that have extremely high conductivity. Silver is the best known conductor other than superconductors. And some folks are saying that graphene and things like that can also have really, really high conductivities. But for metals, silver has about the best. Copper, gold are way up there. Aluminum's even pretty good. So we want to incorporate these things into our model. But how do we do that? We've talked very little about that conductivity term. Is there any other sort of simple way to do this? And is there anything else we need to consider? And it turns out the answer to that is yes, because there is such a strong interaction with the wave, with metals, that there are some special considerations that we need to make here that we don't necessarily need to be as careful about with our dielectrics. So there's four, and there's even more than that, but there's four main techniques that we talk about in this course, how to incorporate metals. The first and the easiest is just use an extreme dielectric constant. Wherever you want a metal, set the dielectric constant to something like 100,000. That will essentially force the field there to be 0. The next thing we can do is assume perfect electric conductors. We'll make another grid, if you will, and put zeros everywhere that's not metal, ones everywhere there is metal, and then what we'll do is we'll just literally force the field to be 0 everywhere there is a metal. Requires a little bit of a change to the code, but not much. The extreme dielectric constant one requires no changes to our code. So as we go down on this slide, we're increasing complexity, but also increasing the accuracy and the power of the method that we're implementing. So the third technique here is actually include that conductivity term. So we have to go back and reformulate our code with that conductivity term. Not such a big deal, but that lets us control what the conductivity is. By controlling, just using an extreme dielectric constant or just a perfect electric conductor, we don't really have a way of saying, yeah, but this material is only partially conductive. So if we include the conductivity term, it gives us the power to do that. Then even more powerful is the Lorenz Drude model. We already stepped through that, and that's a pretty big step. However, we can not only include conductivity, but we can include the dispersion, because the conductivity and dielectric constants of metals very often changes very abruptly with frequency. And since we have already implemented the Lorenz Drude model, we can also incorporate dielectrics that are very dispersive. Well, there's other ways for doing metals. There's Z-transforms and other crazy things. But these are the big four that you can do probably 90% of what you want to do with just these simple techniques here. So let's talk about the extreme dielectric constant. Let's look at our update equations for the electric fields. We see we have the electric field E is equal to the electric field D divided by the epsilon. So if we want to force our electric fields E to be 0, we will just make our dielectric constant something ridiculously large, like 100,000 or 1,000,000. So every time we calculate E from D, we will get a number that's orders of magnitude smaller than anything else, and it'll essentially be 0. So as we make those ridiculously large, we will force the electric field to be 0 at that point where our dielectric constant is ridiculously large. So we don't need to change anything in our finite difference time domain code to do this. So that's really cool, and we can get pretty accurate answers doing this. The next thing we can do is, instead of looking at these as the reciprocal of the dielectric constants, let's think of these as update coefficients. So Ex is simply dx times some update coefficient. Well, what we can do is we can create arrays of our perfect electric inductors for the x components, y components, and z components, and simply just multiply these in. So everywhere this PEC array is 0, our update coefficient will be forced to 0, and it will force the electric fields to be zeros. And anywhere these are 1s, we just have our ordinary update coefficient, which is probably 1 over epsilon. And so no change there. So we really just force our update coefficients to be 0 where we want to force our electric fields to be 0. Requires a little bit of change to the code, but I think in the end it's a little bit better approximation than the extreme dielectric constant, although probably not much different. Well, the third method, and a bit better method, is to actually include the conductivity term in Maxwell's equations and formulate the update equations, leaving that conductivity term in there. And we already did that in a previous lecture for one dimension. And the final one, which we also talked about in the context of one dimension, but used the Lorentz Drude model. So we introduced two sort of auxiliary parameters, but these parameters have physical meaning. We have the material polarization, and then we also have the polarization current. So every point in our grid where we have a material that requires the Lorentz Drude model, we're iterating this P and J in addition to the fields. So our update now looks like this. We update H from E, we handle the H field source, we update J from P and E, then we update P from J, then we update D from H, then we handle the D field, total field, scatter field source, then finally update E from D. And this process repeats itself. This is a bit more computationally intensive than anything else, but it is very powerful. We can incorporate pretty much any kind of dispersion that there is, and our intermediate parameters P and J are things that are actually physically meaningful that we can visualize and potentially learn things from. The other techniques for incorporating dispersion that are maybe a bit more efficient, a bit more powerful, don't give us intermediate parameters that have physical meaning like this. So I think for an academic environment, I really prefer this method for incorporating dispersion. Okay, so now we know a bit how to modify the FDTD code to incorporate metals. The other big thing, which is probably even a bigger deal, is where to place the metals. This isn't necessarily obvious. What we are looking for, we want the field immediately inside the metal, that first component inside the metal, to be a tangential component to the surface of the metal. So for the EZ mode, the electric field is always tangential to metal surfaces. There really aren't any problems. We can place metals really wherever we want them. It becomes a bit more important to consider this for the H mode. And so if we look at all the field components, how they're staggered in the E grid, for the H mode, we see we have this kind of scattering. So where I'm showing gold here is where we're trying to place metals. But notice that first field component on the inside of the metal is actually the normal component. If we go down this side, we see the normal component. This is bad. This will converge very, very slowly. We're going to need very, very high grid resolution to get an answer in this arrangement. This is the correct placement. Notice the field components immediately inside the metal are tangential. Likewise, they're tangential here, they're tangential here, they're tangential here. This is a much better placement for the metals on a grid. We'll be able to get away with a much more coarse grid placing it this way. So a question may come up. Suppose we have a curved metal surface, or it's coming down at a 45-degree angle. Well, you just do the best that you can. I would also refer you to the literature. There's some much more sophisticated ways of handling metals that cross through the middle of a Yee grid cell. This is just the very simplest thing that we can do, but it still turns out we can model a whole lot here, just doing it this simple way. Our last topic is alternative grids. So far we've talked about a Cartesian Yee grid. It turns out there's other choices, and there's reasons we might want to do that. So, first of all, we have a Cartesian grid. So if we have a curved structure, we are essentially approximating those curves with a staircase approximation. That's what we're showing on the right here. So immediately we have one drawback of this Cartesian grid. The Cartesian grid is very simple, but it does not conform well to curved surfaces. We have to go to very high grid resolution in order to resolve that. And we know that there's some field averaging and some other techniques that we can do. But we could also adopt a grid that is not uniform or is not Cartesian that could conform to that much better. That'll be a more complicated code, but it could represent our devices a bit better. Another problem with the Yee grid is that there's additional interaction with the wave in our Yee grid. A physical wave in outer space, there's no Yee grid. And it turns out a wave travels slower on a Yee grid than it would physically. So that makes it look like it's embedded in materials that have a slightly higher refractive index than they would in a physical device. So this tends to push the spectra to lower frequencies than we'd normally expect. So if we look at the dispersion in the lattice, so think of this as a map of refractive index depending what direction a wave is going. So we start at the origin, we pick a direction, and this dashed blue line is what the physical wave would want to see. So it sees the same refractive index no matter what direction it's trying to go. So a wave on a Yee grid, we go out to the red line, and we notice the red line is past the blue line, so the refractive index is slightly higher, meaning it's traveling slightly slower than it should. We also see that this red line does not have a circular shape. It's sort of between a circle and a square. So the speed of that wave actually changes depending on its direction. So this is bad. This is a sort of a numerical dispersion. There's some things we can do to correct it. There's some things we can do to make it better, but it's always there. And so this is another reason we might want to adopt a different grid, because they'll have better dispersion characteristics. One popular one is a hexagonal grid. Now, clearly this will make our update equations a bit more complicated, but if you recall on the previous slide, we had sort of an anisotropic dispersion. We didn't have a perfect square for that red line, or a perfect circle. We had something that looked much more square. Well, it turns out that same shape for a hexagonal grid would look more hexagonal. And so it's actually a bit more spherical than the square grid, so we actually get a bit less dispersion on a hexagonal grid than we would on a square grid. It's more isotropic. There is still dispersion here. It's just more spherical, which deforms your answer a bit less. We can use a non-uniform grid. We can stick with Cartesian, but we can make the spacing between point and point different and vary across the grid. This helps us focus our computer resources in an area where maybe the structure is varying abruptly or the fields are varying abruptly, and we need to go in and resolve that. So this is actually a bit easier to implement than the hexagonal grid and can buy us some efficiency. This does not necessarily lower dispersion, but it does let us concentrate our computer resources where the field is varying most abruptly. If we didn't have a non-uniform grid, we would still always have to resolve the most rapidly varying field, but we'd be forced to have that fine resolution over the entire grid. So clearly that's not very efficient, and a non-uniform grid buys you quite a bit of efficiency with a little bit added complexity to your formulation and implementation. Here's an example of why we might want to do a non-uniform grid. We have some waveguide circuit here. So we have a waveguide coming in, a waveguide going out, and also a waveguide going this way. So clearly, we expect the field to be varying most abruptly in the presence of this waveguide, not out here. So notice what we're doing with the grid. We're making the spacing very tight all the way across. We're also making the spacing very tight here all the way down, and the spacing a little bit tighter here all the way down. So we have a very coarse grid in the corners and a little bit in these middle regions. So we get away with fewer points, but we're still resolving the field where we need to. So in this particular case, it's about 50% more efficient. So that's pretty big for the little impact it would have on your formulation and implementation. Even crazier, we can have our yeast cell not just be square, but be curvilinear. And this is very good, particularly for metals when we have to conform to curved surfaces. So high contrast metals, this tends to work really well. And this minimizes the staircase approximation. Clearly, the impact on your formulation and implementation, this will complicate things a lot more. But if the curvature and the boundaries is really important to resolve in your device, you might have to do this. So instead of curving, we can model things with oblique type of coordinates. And this is useful when we're modeling things that are anisotropic or periodic structures that don't have cubic or square symmetry. They might have hexagonal or some other kind of oblique symmetry. Rather than force that to a square Cartesian grid, we can go to these oblique coordinates, and it's very little impact on the implementation. It's a little bit crazy mentally to think that now we have these oblique coordinates. X, Y, and Z axes are not at 90 degrees, but it does let us model things like that very efficiently. Then the best of all worlds, but clearly the most complicated, is completely irregular, non-orthogonal, unstructured grids. So these tend to look much more like the meshes you would see in finite element method. And in fact, we can do FDTD on that. A huge impact on the formulation and the implementation, but we can minimize our dispersion, we can conform to curved surfaces. So electromagnetically, this is the best, but it will be very slow, and it will be a bit more difficult to formulate and implement. Then one that actually is used quite a bit. Very often we have devices that have cylindrical symmetry, and in the following slide I have examples of these devices. So this is called bodies of revolution, and we can develop our finite difference time domain, as it turns out, in cylindrical coordinates. And we can model cylindrical shaped devices very, very efficiently with this, and it works very well. And so we have a more cylindrical shaped yeast cell, as you can see. So if we develop a finite difference time domain code in this bodies of revolution framework, there's a lot of things that we can model very efficiently. We can model bent waveguides. So imagine this being that phi direction in cylindrical coordinates. Of course, we can model cylindrical waveguides, optical fibers, antennas that tend to have cylindrical symmetry, and horn antennas. Those also have cylindrical symmetry. In optics, we tend to use lenses that have cylindrical symmetry. Parabolic dish antennas, and I could go on and on. There's a whole lot of stuff that have cylindrical symmetry, and we can buy ourselves a lot of efficiency going to cylindrical coordinates. There's even times where if we had a Cartesian grid, we would need a three-dimensional model, whereas sometimes we can model three-dimensional things in 2 dimensions if they have cylindrical symmetry. So, and it would always be good practice to do that if we can.